So we begin this class. Once again, very good day to everybody. This is Computer Communication Networks, and in this class we discuss about congestion avoidance techniques, about DECbit, about RED, random early detection. Then we discuss about QoS, quality of service, about its application requirements. So this is especially for you, my dear students and young researchers, and you can reach me at dr.christoananth@gmail.com. So before beginning the session, once again, let me thank God for giving me this opportunity to deliver this useful session, to share my knowledge among my fellow national, international participants, students and young researchers. We discuss about TCP congestion control, about its congestion detection phase. Then we discuss about multiplicative decrement. Then we discuss about DECbit. Okay, so that is a very important mechanism in the error correction. Okay. Then we discuss about goals of random early detection and how you try to avoid the congestion. Then we discuss about calculation of the average queue length, about the calculation of drop probability, what happens to the average queue size when no packets arrive at the router. Okay. Then we have a pseudocode for the red algorithm. So at regular intervals, I'll be giving you some short videos to discuss the knowledge in our topics. Right. So this is TCP congestion control, where the TCP will be using the congestion window as well as congestion policy, definitely to avoid this congestion problem. Okay. So we assume that the receiver can know or maybe can understand the sender's window size. Okay. So here what we are going to do, it should actually inform the sender, okay, to slow down the data packets it is actually transmitting. Okay. So if the network cannot deliver the data as much fast as it is being sent by the sender, which means that it has to slow down. Okay. So in other words, in addition to the receiver, the network is actually a second entity that determines the size of the sender's window. Okay. So here we'll have the congestion policy, we'll have the slow start phase, where it is going to start slowly increment, that is exponentially to the threshold. Okay. And then if you cannot slow down, then you have to avoid. Okay. So there is a congestion avoidance phase. So after reaching this particular limit, okay, the increment is done by 1. Okay. So here we will have congestion detection phase also. So here we are going to identify the congestion problem. So the sender goes back to the slow start phase or maybe the congestion avoidance phase. Okay. And then we will have the slow start phase in the exponential increment. Last case we saw decrement. Here we have exponential increment. So here every RTT will be the case with the congestion window size will be incrementing the exponentially. Okay. So here we will be having initially CWND, okay, equal to 1, and after 1 round trip time, so CWND is equal to 2 power 1, which is actually 2. Okay. And after 2 round trip time, the CWND will be 2 power 2, which is equal to 4. And after 3 round trip time, CWND is equal to 2 power 3, which is equal to 8. Okay. And then you will have the additive increment. Okay. So the phase will be starting after the threshold value is denoted as SS threshold limit. Okay. So this is the size of the CWND congestion window, which is going to increase the additive. Okay. So after every round trip time, the CWND, the congestion window would be incrementing, congestion window plus 1. And here initially congestion window is equal to I, and after 1 round trip time, congestion window is equal to I plus 1, and after 2 round trip time, I plus 2, after 3 round trip time, I plus 3. Okay. So this is the detection phase, where we will have the multiplicative decrement. So in this case, if the congestion occurs, means the congestion window is actually decreased. So this is the multiplicative decrement. Okay. And the only way that the sender can guess the congestion has occurred is need to retransmit that particular segment. Okay. And here retransmission, you can use it to recover a packet that is assumed to be dropped by the router due to the congestion problem. So retransmission, it can take place in 2 phases. One, when the round trip timer will be times out, or maybe when you get 3 duplicate acknowledgement signals. So in this case, the retransmission will occur. Okay. So this is the first case, retransmission due to timeout. Okay. So In this case, the congestion possibility is much high even. Okay, so the SS threshold would be reduced to half of its current window size, and you have to set the congestion window to be equal to 1. Okay, and start with the slow phase again. Okay, and then case 2, retransmission due to 3 acknowledgement duplicate. So if you have received 3 duplicate acknowledgement, so retransmission can occur. So in this case, congestion probability is less. Okay, so SS threshold value will be reduced to half the current window size. Okay, so set the congestion window to be equal to SS threshold and start with the congestion avoidance phase. In the previous case, we had slow start phase, and here we will be going with congestion avoidance phase. So here you are going to take an example where you are going to assume a TCP control, okay, experiencing the behavior of the slow start. Okay. So at the 5th transmission round with the threshold value of 32, it goes to the congestion avoidance phase and it will continue on and on till the 10th transmission. At the 10th transmission, you will be receiving 3 duplicate acknowledgements, okay, which means that you have to retransmit. Okay. So timeout occurs at the 16th transmission round, and here you are going to plot the transmission round versus the congestion window size of that particular TCP segments. Okay, fine. So this is the DECbit. Okay, we'll have this error correction. Okay, dynamic error correction. Okay, so this is queue length versus time. Okay, so this is the average cycle through which the data is being transmitted. So this is the previous cycle, this is the full cycle, okay, from here till the starting of the next one. So this is the previous cycle and this is the current cycle, okay, and this is the current time that is associated. So overall the total one you can call it as the average time interval. Okay, so this is the TCP congestion control technique, okay, implemented in the routers especially to avoid the congestion, and you have to predict the possible congestion and you have to prevent it. Okay, so that is the thing. So when the router wants to signal the congestion to the sender, it is going to add a bit in the header of the packets that is being sent, and when the packet arrives at the router, okay, so the router calculates the average queue length. Okay, average queue length means both busy as well as idle case. Okay, and plus the current busy period. Okay, so the router will be busy when it is transmitting, otherwise it will be idle, it will not be transmitting. So when the average queue length is going to exceed 1, so the router sets the congestion indication packet, okay, so in the back packet header of the arriving packet. Okay, so when the destination is going to reply, which means that you will be having a acknowledgement signal which will be including a set congestion bit. Okay, so the sender will be receiving the acknowledgement and will be calculating how many packets it has received with the congestion indication bit set to actually 1. Okay, so if it is lesser than half of the packets in the last window, okay, so which means that the window is increased linearly. Okay, otherwise window will be decreased exponentially. Okay, so the technique will be dynamically managing the window in order to avoid the congestion, and here it will be increasing the freight if it is going to detect the congestion, and it will be trying to balance the bandwidth with respect to the delay. Okay. So here this technique, we are actually following this DEC technique. It is not allowing for the effective use of the entire line because you cannot completely utilize that available bandwidth. Okay, so that is the thing. Okay, so besides the fact that the tail has increased in size from one cycle to another, which does not mean that there is always congestion. So that is the problem we'll have. Okay, then we'll go for RED, random early detection. Okay, so that is what you'll have with the active queue management technique. Okay, so you can also call it as random early detection, or maybe random early discard, or maybe random early drop, or maybe random early detection. You can have different names. Okay, so the main reason why you are using RED is to avoid this congestion. Okay, so the main reason why we go for random early detection, okay, so is that passive queue management is going to suffer from this problem, and that is the reason we go with the active queue management to actually detect it and avoid it. Okay, and here using this active queue management technique, okay, using this random early detection, you are going to avoid the problem of the global synchronization. Okay, so once again passive queue management suffers from this problem, and active queue management is going to avoid this problem. Okay, and then The main goal of, once again, another goal of random early detection is to avoid the problem of the lockout. Okay, so short-lived flows will be having this problem of lockout when long-lasting flows will be occupying the buffers of the routers all the time. Okay. So active queue management is once again going to solve the problem. Okay, so here the short-lived flows will get much space in the buffer even, and here it is going to maximize the power function, which is actually throughput divided by delay. Okay. So active queue management is going to handle this buffer queue properly, which means that there will be no packet loss and will be no retransmission of packets even. Okay, so the flow will be much smooth, much fluent even, and the delay will be minimum. Okay. So this is the working of the red algorithm. So here there is two types. One is NQ and then DQ. Okay, so random early detection is going to operate during this NQ time. Okay, where you will have minimum queue, maximum queue. Okay, so this is the entire queue size, and this is the threshold that is associated. Okay, so here it will be corresponding to 1. Okay, so here it will be working at the output port during the NQ time. But do not confuse with the input port, okay, in the architecture. Okay, so here random early detection, it is going to run on the output port, but during the NQ time. Okay, so here random early detection operates on the arrival of every packet which is being received. Hence, there is no periodic time interval in which red is actually invoked. So if the packets are arriving at a lower speed, then the random early detection is invoked at a very low speed. Okay, so if the packets do not arrive, means the red algorithm is not invoked. So that is the thing, only during operation it will be invoked. So the random early detection will be deciding whether the incoming packet should be enqueued or maybe dropped. So only during the time period it will be invoked. Okay, so when the new packet is going to arrive, random early detection makes a decision whether the packet should be enqueued or maybe dropped. Okay, so it makes the decision even if there is much space in the queue. Okay, and it makes the decision because if the enqueuing the packet increases the overall delay or maybe makes the queue full, then it will cause the congestion to occur. Okay, and here if the red random early detection is going to drop the packet before the queue is full, then the sender will know about it indirectly and it will reduce the congestion window size and it will be avoiding the congestion to happen in the future. So these are the components of red algorithm. Normally we will use it to calculate the average queue length, and you will go on for calculation of the drop probability where the packet will be enqueued or maybe dropped depending on the probability, and it will be making a decision making logic even. Okay, and for the calculation of average queue length, okay, so when the packet arrives, okay, so the random early detection will be calculating the average queue length. Okay, so this one you can call it as the exponential weighted moving average, EWMA, which is equal to new average, which is equal to 1 minus WQ Q weight, okay, multiplied by old average plus WQ multiplied by current queue length. Okay, so here new average is nothing but the new average average queue length being calculated in that particular sample. So old average is nothing but old average queue length obtained during the previous sample. Current queue length is nothing but the instantaneous queue length at the router. Then WQ is nothing but the queue weight. Okay, so that is nothing but the weight associated with the current queue length. So default value is set to 0.002. Okay, 0.002. Then we'll go with the drop probability. So when the new average is being calculated, then random early detection will be using drop probability PD, where the minimum threshold, okay, that is being calculated for the average queue length, and maximum threshold is the maximum threshold for that particular average queue length. So you have minimum threshold and maximum threshold that are designated in terms of the average queue length, but not the instantaneous queue length. So instantaneous queue length is nothing but current queue length. So here you will go if the new average is less than or equal to minimum threshold. Okay, so which means that the default value of the minimum threshold here is 5 packets, and you try to enqueue the incoming packet. Okay, so which means that PD is equal to 0. Else if the new average is greater than the maximum threshold, okay, so you will go with the default value of the maximum threshold is 15 packets. Okay, so once again what you have to do, you have to drop the incoming packet, else calculate the PD from the equation. So PD is equal to maximum P multiplied by new average minus minimum threshold divided by maximum threshold minus minimum threshold. Okay, so here you will be having this slope of this linear function will be depending on this maximum p value. Okay, and maximum p is nothing but the maximum drop probability. Here the default value will be considering it as 0.5, but previous case we had like 0.02. So here the new average length of the queue is lesser than the less than or equal to the minimum threshold value, which is actually 5. So here the drop probability would be equal to 0. Okay, so 0 means packet will not be dropped, but it will be in queue. Okay. So here the new average length of the queue is greater than the maximum threshold, which is actually 15. So here in the case the drop probability is actually 1. Okay, 1 means packet will be dropped. 0 means packet will not be dropped, it will be in queue. Okay. So next we will have an intermediate case where the new average length of the queue is between the minimum as well as maximum threshold value. So in this case the drop probability will be calculated. Okay, so when you calculate the value of drop probability, random early detection will be using the logic to decide whether the income packet should be in queue or maybe dropped, whether it is 1 or maybe 0. So here if the drop probability is less than or equal to r, then enqueue the incoming packet. Okay, else you try to drop the incoming packet. Okay, so r is nothing but the uniform distributed random number generated between 0 and 1. So here if you can see minimum threshold, maximum queue length. So here from this one, no drop, random drop, and then drop all. So this is the packet drop probability. So here the left part, as I told you, it is the left part is, as I told you, it is no drop, this is random drop, and this is drop all. Okay, so here if the average queue length is lesser than or equal to the minimum threshold, which means that the packet will be in queue, otherwise it will be drop all. Okay, drop all region. So if the average queue length is greater than the maximum threshold value, which means that the packet will be dropped, and if the average queue length is between the minimum as well as maximum threshold, which means that the drop probability will be calculated. So accordingly the decision will be made whether it is in queue or maybe discarded. So we'll try to analyze whether this PD drop probability is sufficient to enable a uniform random drop pattern. Okay, so here you will be having incoming packets drop all, drop packets randomly, no dropping. Okay, so from this the departing packets will go on. Okay, so this is the maximum threshold and this is the minimum threshold. Okay, so here the average queue size, when it becomes constant, the number of arriving packets between the drop packets becomes a geometric random variable with PD. Okay, so which means that the packet drops are not uniformly distributed, which means that drop packets will be randomly. Okay, so here you will be calculating the drop probability PAC equal to PD divided by 1 minus count multiplied by PD. Okay, so here the count is nothing but the number of packets which are in queue since the last drop. And what happens to average queue size when no packets is going to arrive at the router? Okay, so suppose when since the random early detection is invoked only when the packets arrive. Okay, so there might be a possibility that the average queue size will be incorrectly indicating heavy congestion when actually the queue is actually empty, but it will be showing okay there is heavy congestion. So if it is going to occur, okay, the incoming packet might get dropped even when the queue is totally empty. Okay, so the basic problem is that average queue size does not decay when the queue is actually idle. So this is actually something like a misinterpretation. Okay, so when the first packet is going to arrive at an empty queue, the new average is actually calculated. So new average is equal to 1 minus WQ power m multiplied by old average. So m is nothing but the packets that might have been transmitted by the router if it is not idle. Okay, so from this case m is actually calculated. So here m is equal to idle stop time minus idle start time divided by average time transmission of the entire packets. Okay, so here the average transmission time of the packet is nothing but average packet size divided by bandwidth. Okay, so here you can say that the packets are of different sizes in the network. Okay, so this is the pseudo code for the random early detection algorithm. So when the packet arrives, so step 1, if the queue is empty means you calculate the new average. So new average is equal to 1 minus WQ power m. M is actually might be transmitted. Okay, multiply by old average. Else case you go with the new average is equal to 1 minus WQ power m will not come, multiply by old average plus WQ multiplied by current queue length. Okay. Then you'll go with step 2. If the new average is less than or equal to the month, okay, so you try to enqueue the incoming packet. So else if case new average is greater than maximum threshold, drop the incoming packet. So else calculate the PD as well as PA. Okay, so then you go with step 3. If PA is less than or equal to R, enqueue the incoming packet, else you try to drop the incoming packet. Okay, so you go with the configurable norms. Okay, WQ, minimum threshold, maximum probability, minimum packet, mean packet size.